Or today, lecture 11 is the day before our first exam. First exam covers all of chapter 1 as well as the easier parts, you might say, or the easier kinds of problems from the first couple sections of chapter 2. In the lecture today, I am going to do a derivative example that's going to be a harder example with the definition of the derivative that you're not going to have a problem this hard in exam 1, but it could show up on exam 2, so we want to start practicing with it. And I also want to see in this example that relying on technology, whether it be a calculator or Mathematica, can lead you astray if you're just like numerically approximating derivatives. Sometimes the examples are such that problems actually can occur, whether you just plug in numbers or just make graphs. Then we'll review for exam 1. What I'll probably do is I'll probably just go through the list of things to know fairly quickly. It's kind of a long list if you saw it on the shared drive yesterday. And then I think it would be best to do that quickly and then save time for Q&A at the end. Okay? So as we go through the list, maybe you don't want to take notes except maybe things that I read on the board. You want to just focus on listening. But write down any questions that you might have. And I will try to highlight the things that people sent me as far as their top 3 choices of topics they feel confused about. Not everybody sent me those 3 choices still, even before class here. It really was an assignment, but I realized maybe some of you didn't read your email soon enough, so I will give you an extension on that if you didn't send it to me. Send it to me by tonight, 11:59 p.m., let's say tonight, and you'll still get those points. Okay? Just in case you didn't get the message. And if you're not sure what I'm talking about, then you want to read your email. Okay? All right, so here's a new derivative example. Exam 1 again this Friday. You'll have more time. Instead of starting at 11:10, we'll start at 10:45, so you have extra time. You will need your calculator. It's not a no calculator thing. It's not, can I use my calculator? You will need your calculator. I will probably write 1 or 2 problems where you would specifically need it for something. So I want you to use your calculator for the exam. You may use both sides of a 3x5 note card for any notes you want, whether it be formulas or examples or explanations of things you can put on that note card. Practicing problems is more important than making a note card, however. I always say this, really the note card should be there just to reduce your anxiety. Okay? You should practice enough problems that you know the material well enough that you don't really need the note card. Okay? That's how you should view it, because the people who rely too much on the note card usually don't do very well. For one thing, if they're relying too much on the note card, they don't really understand it as well as they should. For a second thing, you rely too much on your note card, you spend too much time like searching through your note card, you start panicking, time's going by, you don't finish in time. Okay? So you want to be able to do it without a note card. It's really there mostly just to reduce anxiety. Other important things to take care of are for your own personal care, nutrition, eat well. It is important. Okay, eating junk food definitely is not good in terms of thinking. Sleep, of course, is also really important. Don't stay up all night long. It's not a good idea, even in studying for the exam. Prayer and your relationship with God. Okay, prayer does help. Okay, so spend time in prayer, spend time in the Bible, spend time talking with the Lord and asking for strength and reduction in anxiety. Peace, if you're at peace, it's definitely going to help you for the exam. And help and care for each other. You've gotten chances to meet people in the class if you didn't know anybody. You're working on the graded problems. So if you find somebody else good to work with, go ahead and work with them. If you need help, go seek help out, either from me or from Math Lab or from your classmates. And if you are somebody who feels like you understand stuff well, care for your classmates and help them. Okay? And when you teach somebody, that even reinforces ideas in your own mind that might be still a little bit vague. Okay? All right. So let's do this example. And again, this is a more complicated example than will show up on the exam 1, but it could be on exam 2. But first of all, a reminder of the definition of the derivative. Given a function f, defined at a number a, x equals a, so a is some specific number, okay? So in your imagination, pretend a is 3 or something. And near a, you want f to be defined on some little interval at least, near a. The derivative of f at x equals a is denoted by, again, f prime of a is what you say, and you put that little apostrophe in there to indicate the derivative. That's not a typo, that's essential. And it's defined by the following limit if the limit exists. And I dispensed with the delta x here and just used h. Okay, so it's the limit as h goes to 0 of this thing. This thing has a name, by the way, it's called a difference quotient, because there's a difference and it's a quotient. Okay? When you hear the name difference quotient in calculus, it's referring to that expression right there. For any fixed h, and again, you think of a as fixed, it is a slope of a secant line. For any fixed h, think of h as being a distance if it's positive, the coordinates of this point are a, f of a. The coordinates of this point are a plus h, f of a plus h. That's rise or run if you ignore the limit sign. That distance right there is f of a plus h minus f of a. This distance right there is h. This is the rise, this is the run. That's rise over run. It's a slope of a line connecting these points right there. That's called a secant line. It's not the same thing as the curve. The curve is down here. This is a straight line. Secant line. Not a tangent line, a secant line. But as h goes to 0, as this point moves to the left toward a, then the secant line, you can sort of imagine, becomes the tangent line. In the limit as h goes to 0, we say. The tangent line is the one that just kisses the curve, so to speak, at the one point. Better way to say that is, if you zoom in closer and closer to the point, the curve is going to look more and more like the tangent. That's a better way to describe it, actually, than just the kissing idea, because that can be misleading. Because the curve could come back down over here, then your tangent line could cut it again over here. So don't let that mislead you. If it crosses the curve again over here, it's still a tangent line right there. It's not like a tangent to a circle that only touches it at one point. Question?
What if the function is not a quadratic, so then the derivative would not be a line?
Good question. Then we consider lots of other examples after exam 1, including an example here today as well. We have to do this for lots of examples. That's part of the point of calculus, is to learn how to do it for other examples. Again, this is also described as the instantaneous rate of change of f at x equals a. The slope is the rate of change. It is almost plus the slope of the tangent line. The steeper the line is, the steeper the tangent line is, say with a positive slope, the faster the function changes. If you imagine, again, the red dots, I won't show you that animation again, but imagine the red dot along the horizontal axis moving to the right at a constant speed. The corresponding vertical dot, representing the second coordinate of the point on the graph, if the graph is concave up like this, will speed up faster and faster. And at any moment in time, the derivative, which is the slope of the tangent, tells you how fast that dot is moving on the vertical axis. At least if it's moving upward. If it's moving downward, it gives you the opposite, the negative of how fast it's going. So like a velocity, positive and negative direction in that case. We'll talk about that more next week. And I've already talked about the geometry. All right, on to the example. This is an example where numerical and graphical approximations break down. So you had some homework problems where you think about graphs and numerical approximations, but they are kind of a problem in this example. F is going to be the square root function. F of x equals square root of x. I'd like to find the derivative of this function at 4. That's the goal. Find f prime of 4. Okay? So we're going to go ahead and do that from the definition of the derivative. You should be able to use the definition of the derivative on the exam, though for simpler examples like x squared, x cubed, maybe 5x plus 4x squared, something like that. it's a little bit more complicated, you should try practicing something like that. If a function is, for example, 5x plus 4x squared, okay? Or some other combination like that. But this one's trickier. By the definition of the derivative, you can write this. So the a is 4. Okay? And you should know this is because of the definition of the derivative. Probably not in this exam, but perhaps on exam 2, I will have you give reasons for each step. This first thing is the definition of the derivative. The second step right there, that's just using the formula for the function. F of 4 is the square root of 4, which is just f of 4 plus h. I look at the formula for the function, I need to replace x by 4 plus h. The function is square root of x, so this is the square root of 4 plus h. That's just what the function is. That's the reason. This limit, though, looks kind of difficult. How in the world are we going to calculate that limit? What do you do with the square root? It should feel kind of difficult. So instead, you might try approximating. Get rid of the limit sign and just write the fraction. The limit should be approximately equal to the fraction when h is small. And when I say h is small, what I mean is close to 0. But not equal to 0. We can't plug in 0 here because we'd be dividing by 0, and we don't want to do that. Okay? This is a fundamental basic idea that you should understand for the first exam even. You can approximate a limit like this by plugging in a number close to c. C in this case is 0. Look at a number h close to 0, but not equal to 0. This function is not continuous at h equals 0. If you graph it, there's a hole in it. I'll show you a graph in a minute. But what happens when you try to do this? Here's the approximation from the previous slide. Here's a table of values that I made with Mathematica. Something interesting. Do not write down this entire table, just look at it. I'm trying smaller and smaller values of h. 0.1, 0.01, 0.001, etc., 10 to the negative 6, 10 to the negative 7, etc. You see the value of this fraction getting closer and closer to 0.25. It seems like the limit is 0.25, and then all of a sudden, what in the world? What's going on there? It's called numerical error. Machine error. It's because of the fact that our computers, our calculators are really finite things, and we're really trying to do something that is related to infinity. Letting h get arbitrarily close to 0, in a sense, I can get infinitely close. I can keep making these negative exponents bigger and bigger. 10 to the negative 100, 10 to the negative million, 10 to the negative billion. And h would still not be 0. But the technology is having trouble in the approximation. It's a finite machine. It can only do finite machine arithmetic. It starts making mistakes. I'm serious. Mathematica is making mistakes here.
How can I help?
Did I say Siri or what? I said seriously, didn't I? Did that happen before? Gotta stop saying that word. I tried in my calculator, similar anomalies happen. The answer is 0.25. But if you keep trying smaller and smaller values of h, you run into trouble. I mean, these are really small, so you probably wouldn't try those. You'd probably try values more like this, and you'd happily say the answer is 0.25 and you'd be right. But just realize it's possible for things to go wrong. Here's a graph. The graph is even wilder. Here's what it looks like. Well, okay, this is not such a wild graph. Here's what the graph looks like, letting h go between negative 1 and 1. This is the graph of the thing I'm using to approximate the derivative as a function of h. That's okay to do. I can graph it as a function of h. This is not the original function. This is not the square root function. This expression, that's approximating the derivative. It's got a hole in it. It's undefined at h equals 0. But watch what happens as I zoom in near 0. See that? What in the world? It's not the same thing as what I showed you the other day with the infinitely oscillating sine function, sine of 1 over x. That graph I showed you the other day was accurate. This graph is inaccurate. The numerical approximations are having difficulty. It seems like it's oscillating infinitely often, but it's really not. It's also a little confusing because you see a bunch of 0.25s here. That's because the value is so close to 0.25 that Mathematica is just, in a sense, rounding all the numbers on the vertical axis there to be 0.25. Because it's so close. But they're jumping all over the place. Mathematics is trying to graph it. It's graphing whatever it computes, but it's computing wrong numbers. So what do? Instead, you take an algebraic approach. You have to try to calculate it by hand. That confirms the answer truly is 1/4. But it is tricky. The trick involves rationalizing the numerator. Wait a minute. I thought you could only rationalize denominators. If you thought that, well, you thought wrong. You can rationalize numerators. You're used to rationalizing denominators. We've talked about this before. You got something like this. Your teacher told you, hey, we don't like square roots in the bottom there. Multiply the top and the bottom by square root of 2 and write the answer this way. Rationalize the denominator, the bottom. Make it not a root. I told you back with the trig section that actually both of these numbers are fine. They're both equal to each other and they're fine answers. Rationalizing or having roots in denominators is not a mathematical sin. Just felt like that way from your teacher. At least it felt that way from my teacher when I took the algebra in 8th and 9th grade. Okay? They do it this way for two reasons. One is that it just sort of puts the answer in a more standard form, so it's like easier to check. And two, it is a useful technique. But in this case, it's going to be the numerator that we try to rationalize. We try to get rid of the square root in the numerator. How? There's the trick. Multiplied by this disguised form of 1. Which, you know, you look at that and you'd say, I would never guess to do that. And that's probably the case, but I'm telling you, do it. Okay? Why did I put a plus sign there instead of a minus sign? What am I trying to do here? I'm trying to get rid of the square roots in the top, in the numerator, and trying to rationalize the numerator. And if I multiply the top by this expression, imagine with me here, foiling here. First times first is square root of 4 plus h times square root of 4 plus h, which is just 4 plus h. The square roots go away. Outside times outside is still got a square root, 2 square root of 4 plus h. Inside times inside also still has a square root, but it's a minus 2 square root of 4 plus h. The outside and inside products cancel. One's a plus, one's a minus. Then last times last is negative 2 times 2 is negative 4. The square roots completely go away in the top. But what about the bottom? If I do it to the top, I also have to do it to the bottom, and the square root doesn't go away in the bottom. So how is this helpful? We will see that it's helpful here in just a minute. Because it makes it possible to solve the problem. That's why it's helpful. It doesn't matter that there's a square root in the bottom. It's okay. Simplify the top, cancel the 4s, and now you see the magical thing happen. We can divide out these h's, including the h in the bottom, which means we're ultimately going to be able to evaluate the limit by plugging in h equals 0. This function of h is undefined at h equals 0, but it equals this function of h everywhere but 0. This one is continuous at h equals 0. I can evaluate this limit just by substitution. The answer is 1/4. Okay, so again, this is a trick. It's tricky. When you see these tricks enough, you start getting a good feel for what they should look like. It takes the teacher telling you, first of all, and then practicing. Reasons for each step. Definition of the derivative. Formula for the function, it's the square root function. Multiplication by 1. This is essentially just a big 1, doesn't change the function. Simplify, that's just algebra. Continue to simplify, more algebra. This is more than just algebra here, this equality. This is also based on the fact that the value of the limit is independent of what happens with the function at h equals 0 in this case. This function is undefined at h equals 0, but it doesn't matter. This one does have a limit. It's continuous at h equals 0. I can now substitute h equals 0 in there. That's the continuity of this function of h at h equals 0. That's the reason for this equality. Continuity. And then simplification. Okay, so again, for the first exam, you're not going to have to give reasons for these kinds of things. But I think probably for the second exam, you'll have a problem perhaps similar to this, where you have to use this technique and you have to give reasons for each thing. We will go over it again next week and probably the week after as well. We'll do more examples like this. Okay, so review time. So again, I'm going to go through this list. So there's going to be no break today. I'm not sure if we'll be able to finish early or not. I'm guessing not. So take a little 10-second break here just to loosen your shoulders or something. So I'll go through the list. It's a big, long list of things to know. It's essentially all of pre-calculus that we overviewed in the course of the 3 weeks. Again, as I go through it, think of questions you have. I will try to pause on the things that people said in their email response. It was typically more difficult for them. I'll try to spend more time on that, on those things. Describing this as facts to know, concepts to understand, and skills to have. Slide number 1. There's 5 slides total. First thing, function notation. In other words, you should be able to simplify things like f of a plus h. This is often a point of confusion for people. I know from past experience in giving exams like this. Often the case that maybe 25% of the class doesn't know how to deal with expressions. Whatever's inside there, that's what you replace the x with. Which in this example right here means you need to square this entire expression. Which does not give you a squared plus h squared. You got to FOIL. It's a plus h times a plus h. A squared plus 2ah plus h squared is what you get. But at the most fundamental level, you need to understand that this thing right here, f of a plus h, is, for this function, a plus h quantity squared. Equations of lines and linear functions. There's the point slope form. Either of those two forms is fine. I actually prefer the second form because it's quicker to get the y as a function of x. It already has it, whereas with this form, you have to do another step of adding y0 to both sides. I prefer using a subscript of zeros, but your teacher may have used ones. It doesn't matter. The symbols don't matter. It's the idea that matters. So if I give you a point and a slope, you should be able to find the point slope form of the line, or you should be able to solve for y and get it in the slope intercept form, like that. Which means if you've got it like this, then you've got to multiply the m through the parentheses and simplify. Or maybe you know a couple points on the line. There's another thing that could happen. I give you a problem with a couple points. The first thing you have to do is find the slope, the rise over the run. And then you either use point slope form, or you go right away to slope intercept form and you solve for b by plugging in one of the points. That's another approach people often use. Any of those approaches is fine as long as you don't make a mistake. Okay? be able to find and interpret the formulas, including the meaning of the slope and the intercepts. So I'm trying to imagine an application here. Basic kind of application might be that f of x is your profit as a function of the number of widgets you make. Widget, again, just being a generic term for some item that we might manufacture. Profit is revenue minus expenses, so profit can be negative, which means you're losing money. If it's positive, then you're gaining money. The profit formula function could look like that. Could be a straight line, at least approximately. And the slopes and intercepts have meaning. The slope would tell you how much extra profit in dollars you get for every extra widget you make. It says widgets, W-I-D-G-E-T-S. That would be the meaning of the slope. And the intercepts have meaning as well. This intercept, the y-intercept, tells you what's your profit when you make 0 widgets. It's negative, and that means you lose money. And that's telling you how much money you lose. This intercept has meaning. It's telling you the break-even point, how many widgets to make so that your profit is 0. And then if you make more than that number of widgets, then you make a positive profit. That would be an example of a basic application where interpreting the meaning of the quantities is important. The meaning of the slope of the units of the slope are always units for the y per unit of x, no matter what the situation. Because it's a rise or a run. Y, change in y or change in x. So it's got to be the units of y divided by the units of x per unit of x. Be able to graph them, recognize the data as linear or not. Remember, I had that class period where I made a table of values, and we saw that the linear situation, when x increased by 2 every time, y kept increasing by the same amount, or decreasing by the same amount, changing by the same amount. That's a linear kind of pattern. We'll talk about exponential in a minute. 5 minutes right now. What about exponential functions? People on the email were asking a little bit more about exponential functions than linear, certainly. There's this initial value and growth/decay, factor/rate base form. That's a confusing combination of words. What do I mean there? I mean this form. A is the initial value. And notice I'm switching to using t for the independent variable here. I decided to go ahead and do that because the most common application of exponential functions is the independent variables to length. Exponential growth, exponential decay often is over time. Not always, but often. So I went ahead and used the t. The initial value is what you get when t is 0. When you plug in 0, you get d to the 0, which is 1. A times 1 is A. A is the initial value. What about the growth/decay factor? That's the B. That's the growth/decay factor. Why do I call it growth/decay? Because it can represent either. It's growth if b is bigger than 1, and it's decay if b is less than 1. Technically, you don't want negative b's, so really b is between 0 and 1 for decay. And it's easiest to think about in terms of percentages. That's where the R comes from. R is the growth/decay rate. Factor versus rate. For example, if B is 1.05, that's equivalent to R equaling 0.05 or 5%. That's 5% growth in Y per unit of T. Say T is time, that's per unit of time. So for example, if this function represented exponential growth of your money in a savings account, Maybe your initial balance is $1,000. Your balance would grow by 5% every year. The next year it would be $1,050. That's 5% growth from 1,000. The next year grow by another 5%. 5% of 1,050, I think is $52.50. You'd have $1,102.50, I believe, would be the amount after 2 years. That's 5% growth. You could also, again, think in terms of factors. You multiply each of these numbers by 1.05 growth factor to find the next value. Zoom in if you need to. It's not right enough. Can you guys all see this too? Okay. On the flip side, B could be between 0 and 1, like 0.9, and R could be negative. R would be negative 0.1 in this case, negative 10%. What's an example of something that decays exponentially? Well, radioactive decay is one example. Another example is actually your car value. It's called depreciation. You buy a car, new car, you drive it off the lot, it instantly loses $2,000 worth of value. Did you know that? Even if it was used as a demo car or a test drive car before you bought it, they still charge you the same amount, but when you drive it off the lot, you have owned the car for a minute, you lose a couple $1,000s of value. It depreciates. And depreciation is often modeled as exponential decay, and it's reasonably accurate to model it that way, except for the first minute. But after that point, it's reasonable to model as exponential decay. This would represent 10% loss of value every unit of time, like every year perhaps. Probably for a car, it's more like 20%. And it's negative. That's representing decay. There's the initial value and continuous growth/decay form with the number E. And this new letter K. K is called the continuous growth rate, growth/decay rate. K is more analogous to R than it is to B. I haven't really explained what the continuous growth or decay rate means. We'll talk about that more in chapter 2. For the moment, you should just be able to compute it using these equivalencies here. If you know K and you want to know B, use this equation. B is e to the K. You can also solve for R. R is B minus 1, which is e to the K minus 1. On the flip side, if you know B or R and you want to know K, then use these equations. Equivalent logarithmic equations. Essentially, take the natural log of both sides of this. Natural log of e to the K is just K. Natural log of B is natural log of B. And again, K is more equivalent to R than it is to B. If R is positive, then 1 plus R will be bigger than 1. And the natural log of something bigger than 1 is positive. K will be positive. On the other hand, if R is negative, then 1 plus R will be less than 1. Natural log of a number less than 1 is negative, actually. And K will be negative as well. Be able to find and interpret the formulas. Also be able to interpret the meaning of the initial value, growth factor, /decay factor, and growth/decay rate in the way that I described. And if you look at the sample exams on Moodle, I forgot, did I put 1 or 2 exams on? I think I put 2. Yeah, 2 sample exams on Moodle. You'll see problems involving this stuff. Right? It's a pretty fundamental thing to know. Exponential decay and growth problems to solve them. And be able to solve them. You know, like if you want to solve an equation like this, 5e to the 3t equals 7. Well, we're jumping ahead here and talking about logarithms. Divide both sides by 5 first, write it like this. Then take the natural log of both sides. Natural log of e to the 3t is just 3t, because natural log of x and e to the x are inverse functions. On the left, that's natural log of 7/5, which you can leave like this, but you also, if you want, could use a property of logarithms to write it as natural log of 7 minus natural log of 5. As far as your calculator goes, it's probably better to leave it this way, if you want to approximate it. Divide both sides by 3. This is 1/3 natural log of 7/5. And that will be a small positive number for the answer. Then be able to graph them. Know what the graphs look like. Exponential growth looks like that. So B is bigger than 1 here, R is bigger than 0, K is bigger than 0. And exponential decay looks like this. B is between 0 and 1, R is negative, and K is negative. We also talked about doubling time and half-life. You should look into that as well, even though I didn't put it on the slide. I'm sure you're comfortable with that.
What section is that?
1.2. Limits, continuity, and smoothness. You should know that in the case of exponential growth, you can say this. Plus infinity here, this is exponential growth. And also this. Horizontal asymptote at y equals 0 when t goes to minus infinity. And for exponential decay, it's this right-hand limit as well. As t goes to plus infinity, I should say, that's 0. And the one as t goes to minus infinity is plus infinity. That's what I mean by knowing the limits. Then the graphs are also continuous and smooth. Slide 2, quadratic functions. Our standard form, f of x equals ax squared plus bx plus c. Vertex form, f of x equals a times, in parentheses, x minus h quantity squared plus k. Really, k is, let's see, no, k is not the same as c, sorry about that. That's why I use a different letter. And you should be able to transition back and forth between these two things. If I give it to you in vertex form, you should be able to convert it to standard form just by multiplication and simplification. FOIL x minus h times x minus h. Then multiply by a, and then add k, and then simplify. To go from the standard form to vertex form, you've got to use the method of completing the square. So if that's something rusty for you, we did talk about that. That's something to practice. Quadratic formula helps you find the roots when the function is in standard form. There's the roots. I will not sing the song again. You've seen this many, many times, I'm sure. And application. Physics, free fall. So the height of some object is a function of time. When you assume there's no air resistance or very little air resistance, then we'll get a quadratic function of time. We call it h of t for the height function, if you like. Or maybe h equals f of t, that might be better, but it turns out the a equals negative g over 2, where g is the acceleration due to gravity. In standard units, that's 9.8 meters per second. In feet per second, it's 32. You don't need to know those numbers. I would give them to you if you need them. Plus the initial velocity, it turns out, times t, plus the initial height. Call it y0. V0 represents the initial velocity. Y0 represents the initial height. Initial velocity can be positive or negative. the upward direction is positive. If you have a ball in your hand and you throw it straight upward, then the initial velocity is positive. If you throw it straight downward, then the initial velocity is negative. If you drop it, then the initial velocity is 0. And again, g is the acceleration due to gravity. I have to give that to you. You should be able to use a function like this, for example, to figure out when the ball hits the ground again. Set this equal to 0, solve for t. Use the quadratic formula. That's how you do that. As far as the two coupon bonds, I didn't really explain those in as much depth as might be helpful because I didn't have time. But probably if I do ask you for a yield rate for a two coupon bond, I give you the equation you need to solve, and I just be testing can you use the technology to solve it. Use the quadratic formula, or maybe graph it and find the intercept. Okay? Since I didn't have a ton of time to explain the idea of a bond. Transformations of functions, especially for quadratics and trig functions. So that would be, I'm not getting into more detail here, that would include horizontal translations. Replace x with x minus h. Vertical translations. Replace f of x with f of x plus k. Just saying these verbally here for the sake of time. There are also vertical and horizontal stretches and compressions. It's the horizontal stretch and compressions that are the most confusing, I think, for people. Horizontal one is where you multiply the input of the function by some number. And it's a compression when that a is bigger than 1. And it's a stretch when it's less than 1, which is confusing. People tend to think of it as the opposite, right? But you can always plot points to help you confirm it if you're feeling confused in the test. There's also reflections across the horizontal axis and the vertical axis as well by appropriate multiplication of -1 in an appropriate spot. We'll see this play out with trig functions because I'll spend a little bit more time with trig functions because that was a common thing people put in their emails. One-to-one functions, function composition, and inverse functions. People often wanted to know more about inverse functions in the email. For a relatively simple example, we can take a linear function like 5x minus 2 or something and say find the inverse function of that. You should be able to do the mechanics, which is not too hard in this case, but you should also understand the idea. Let's do the mechanics first. Essentially, you're just trying to swap the roles of x and y. You're trying to solve for x as a function of y. This is y as a function of x. So add 2 to both sides. We're trying to isolate x. Then divide both sides by 5. X as the inverse function of y would be y plus 2 over 5. 1/5 y plus 2/5. And again, technically speaking, that's fine as the inverse function formula. You do not have to swap the variables. And in fact, I really emphasize that if the variables mean something in real life, you should not swap them. That would be a bad idea because then you'd be swapping the meaning. We swap them again for 2 reasons. One is because we're kind of more used to having x be the independent variable. And the second reason is because of that nice reflection property. If you do the swapping and graph both functions in the same axes, there'll be reflections of each other across the 45-degree line from the origin, y equals x. The first function is going to have a graph looking about like this. Slope of 5, vertical intercept of -2. Pretend that's straight. And the inverse function is going to give a reflection. You kind of got to imagine turning it at a 45-degree angle. It's a bit difficult, even for me. something about like that is going to be what it is. This is going to be -2 there. So this is f of x, and this is f inverse of x. Slope of 1/5 and a vertical intercept of 2/5. What's the idea behind it? Let's talk about the idea in the context of logarithms. Say we take our case of base 2. I'd like to solve that equation for x. What value of x will give me a y, an output of 8? This is the graph of y equals 2 to the x. Here's 8. I'm turning the roles of x and y around still. Instead of plugging a number in for x and finding the output, I'm saying, give me the output, what's the input? What is x? There is some x. You can see just from the picture. And in fact, it's a unique x because this function is 1-to-1. It passes the horizontal line test. Every horizontal line goes through it at most once. So that x is just one value. There's a unique x that you can plug into this function to give you an output of 8. We call that value of x f inverse of y, f inverse of 8 in this case. It definitely exists. Moreover, in the context of this situation, we call it log base 2 of 8. This logarithm idea is just, it's an inverse function. Name is kind of weird, we just have to live with the name. So in general, d to the x equals y is equivalent to x equals log base d of y. When you compose a function and its inverse, you get back the original input. Sometimes you have to restrict the domain. With the exponential functions, there's no need to restrict the domain. That comes up most commonly for us with quadratics. It's not 1-to-1. Restrict the domain. Either think about just this piece or just that piece. And it also comes up for us with trig functions. For example, the sine function is not 1-to-1. But if we restrict the domain appropriately, we can pick up a piece on which it is 1-to-1. For the sine function, that's a piece where x goes between -π/2 and +π/2. That's how we restrict the domain for the sine function to find its inverse. It's not telling you how to compute the inverse, though the reflection property gives you the graph and would allow you to estimate the values of the inverse. But our technology is still able to compute those values. We will do some more with trigonometry here in a bit because people asked about that in the email as well. How they found it in an example, a linear function and a logarithm. We did some other examples in past classes, like a rational function where the top and the bottom are linear. We did an example like that back in lecture 4 or something like that. How are the graph domains and ranges we talked about the reflection property? Domains and ranges get swapped. If we're considering this piece of the sine function, whose domain is -π/2 to +π/2, and whose range is -1-to-1, for the inverse function, inverse sine, the domain becomes -1-to-1, and the range becomes -π/2 to +π/2. And the graph ends up looking about like this. Inputs between -1 and 1. Zoom in if you need to with the camera. That's -1 right there. Inputs in there. Outputs between -π/2 and +π/2. This is +π/2 right there. and negative pi over 2 down here. So the domains and ranges get swapped between a function and its inverse. Same kind of thing happens with exponentials and logarithms. The domain of an exponential is all real numbers and its range is all positive numbers. Whereas with the logarithm, the domain is all positive numbers and the range is all numbers. We need to go a little faster here. I'm going to skip this decompose. There is a question on at least one of those old exams about decomposing, and there was a homework problem, but I think I'm going to save that for a later exam because I don't have time to talk about it. Talked about logarithms already a bit. You should be able to compute special values in special cases like log base 2 of 8, for example, or log base 2 of 1/8 would be negative 3. Because 2 to the negative 3 power is 1/8. Log base 2 of 1 is 0. Those kind of things. Graphs, limits in continuity and smoothness. With the logarithm here, the limit as you go to plus infinity is plus infinity. It grows above any horizontal line, though very slowly. The limit as x goes to 0 from the right is minus infinity. The graph goes down forever and ever below any horizontal line. Properties and proofs. People asked about proofs in the email response. So let's do a proof. Let's prove this one. Log base, let's pick a particular base. Let's say log base 10. Let's do log base e. Let's do natural log of a to the p equals p natural log of a. A is positive, p is any number. Okay, so again, it's good to start proofs with what you know. By the way, there will be no epsilon delta proofs in the test. Those are too hard for us, okay? Wanted to give you a homework problem on it, but no, nothing on the test with those. So here in this kind of proof, start with what you know. What do I know? I know what natural log means. Tease that out in relationship to the symbols that you see. You could say by definition of logs, and by the way, you should write incomplete sentences, though abbreviations are okay. I want to say all the time, so I'm abbreviating definition. I really shouldn't just say logs, I should say logarithms, so I'm really abbreviating there too. We're talking ln, base e. E to the, for example, natural log of a to the p is what? A to the p. Here we know that. That's what a logarithm means. You don't have to prove that. That's the definition of a logarithm. ln of a to the p is the number to which e must be raised to get a to the p. So if you raise e to that number, you get a to the p. And what other logarithm do we have involved? Here we have natural log of a. E to the natural log of a equals a. All right, so you've stated essentially what you already know. You're trying to conclude that these two things are equal. Natural log of a to the p is p times natural log of a. It's not clear how to get there. You've got to tie and to use something else to get there. And with logarithms, you always use a property of exponents because they're so intimately connected to each other. You can just say by a property of exponents, what kind of property might I want to use? Well, here you see an e to the natural log of a to the p. Here you see an e to the natural log of a. It maybe we should try raising e to this thing with the p in there. E to the p times natural log of a. That's got to get in there somehow. What property do you think I should use? Any idea what I'm referring to here by property of exponents? Here's a little hint. Something, something, something. What should go down here? E. It's a little less clear what should go here and here, but think about the fact that you know this is true, and that might be useful for simplification. What should go there? What would be the most useful thing to do? Natural log of a. And put the p out here. Let me get rid of those circles now. Because now, yeah, that thing in the parentheses simplifies just to a. You're almost done. This equals this, but also this equals the same thing. These are the same thing. E to these powers equals the same thing. Therefore, the powers must be equal. And you're done. Technically, you should give one more reason. You should say, since e to the x, say, is a one-to-one function, since you've got the outputs equaling the same thing, the inputs must have been the same thing. Ln of a to the p must equal p times ln of a. Praise the Lord. Okay? So for this kind of proof, start by using what you know about definition of logarithms. Then use a property of exponents in some, kind of creative way. You gotta be careful how you use the property of exponents. Then use the fact that the corresponding exponential function is one-to-one to conclude that the exponents must be the same thing to get your final conclusion. You should practice some more examples with the other properties. On those old exams, there were some proofs involving something called the intermediate value theorem as well, but that was something we did not do in class, so it's not going to be on your exam. I might do an example next week, and we're going to get the second exam. It's worth doing. It's worth talking about. I already talked about an application. Trig functions. Oh wow, 10 minutes. I'm lingering again on these things that people wanted to spend more time on. This is one of them as well. There's the unit circle definition, special values, graphs, the Pythagorean identity. Very quickly, you've got an input for your trig function. You think about thinking of that input as, say, an angle. Call that angle theta. Since it's the unit circle, if theta is in radians, it's the same as the angular, it's the same as the arc length of this arc here. That's also theta. This is the unit circle. Not just an angle measure. And the cosine of theta is the first coordinate of that point, and the sine is the second coordinate. From that, you can quickly get the graphs of cosine and sine, which are, even though you can get your calculator to graph them, it's probably worth just memorizing what they look like pretty quickly. That'll save you time. And if you know special values, you should be able to find those and use the unit circle to help you remember them. The Pythagorean identity is based on the fact that the equation of the unit circle is this, and so therefore cos squared theta plus sine squared theta is always equal to 1. Very important identity. It's not an equation to solve, it's always true, no matter what theta is. That's where you call it an identity. Sinusoids and their graphs. Given a graph, find a formula. Here's your general formulas. We'll talk about this in a second here. Let's take one of these. Say your graph looks like this. Just a piece of it, say, and this is maybe the point 2, 8. This is the point 8, 1. And then over here, we're back up to, it would have to be 14, 8. The period of this is the peak-to-peak horizontal distance. That is going to be 12. So the b is going to be 2 pi over the period, 2 pi over 12, which is pi over 6. The vertical shift is the y-coordinate of something called the midline going through the middle of the graph here. Halfway between the extreme values, the maximum and the minimum values are 8 and 1. Halfway between them is 4.5. That would be the C. Horizontal shift, if you're going to use a cosine, it is 2. That would be the H. And the amplitude is 8 minus 4.5 is 3.5. So a quick formula for this would be y is 3.5 cosine of pi over 6 times, in parentheses, t minus 2 plus 4.5. Then you could, for example, solve for t when you set this equal to something, say 7, using an inverse cosine function. You want to isolate the cosine on one side by itself, and then take the inverse cosine. It would only give you one spot where it equals 7, though, if you do that. I think on one of those old exams I had them solve for one answer, and I gave a little extra credit if they could find the second answer. If I do this for you guys, I think I'll probably do the same thing. Solve for one answer, and then if you can find a second one, give you a little extra credit. Okay? You'd be using the inverse cosine function. Finding all of them involving 2 and pi terms is just too much work for an exam. Should quickly review the domains and ranges of the inverse trig functions. I guess I already did with the inverse sine. An application to solving trig equations like this. The absolute value of A is the amplitude. B is called the angular frequency. Again, it's related to the period. It's 2 pi over the period. The period is also 2 pi over b. H is the horizontal shift. C is the vertical shift. Power functions. Okay, we're almost out of time here. Let me just go pretty quickly through this. I think what's worth emphasizing, say, in the course of about 2 minutes here before we take a short Q&A, is just graphs of rational functions. They're asymptotes, they're both vertical and horizontal. And their continuity, like do they have removable discontinuities? Let's go ahead and already have these in factored form, so just like that, say. You can cancel the x minus 2's to get this, as long as x is not 2. Let's quickly think about the graph here now. I made the degree of the top and the bottom the same, whether you think about it in the original form or the simplified form. Therefore, you are going to have a horizontal asymptote, and I made it so that it's nice. It's y equals 1. Because the ratio of the coefficients of the highest powers of x are the same. 1 divided by 1 is 1. As far as confirming that with limits, properties of limits, you want to probably rewatch that part of Monday's lecture where I showed you how to do that. That came up on today's assignment as well, using properties of limits. There is a vertical asymptote at 4 because the x minus 4 did not cancel. So at 4, there would be a vertical asymptote, and the function definitely would be discontinuous there. There's an x-intercept at x equals -3. Not at 2. The function's not even defined at 2, the original function. There would be a hole in its graph at 2. What does the graph look like? Well, evidently, since it's got an x-intercept over here, it must be going up toward the horizontal asymptote over there. It must be going down toward this one, this vertical asymptote here, with a hole in the graph right about there, say. And up here, I bet it's doing this. Now, you can plug in numbers to check the signs of these things to make sure you're above 1 here, for example. Plug numbers in. X equals 5, for example. It should look like this, I'm pretty sure. It's not continuous at 2, but it is a removable discontinuity, which can be removed by taking the limit of this one, the simplified form, as x approaches 2, which would be 5 over -2, -2.5, I guess. With the second coordinate of that missing point. If you filled in the hole, that would make it continuous. The limit exists because the two-sided limits both exist and are equal to each other. Then we have information about, continuity and derivatives. Again, as far as epsilon delta goes, there's no proofs on the exam. There was an old problem on one of those exams about finding a window in which the graph exits the horizontal side of the window. That's related to epsilon delta. I think for sake of time, I probably will not put any epsilon delta stuff on the exam because we haven't had time to talk about it at all. Not just proofs, but probably nothing at all. But you should know the algebraic properties of limits and be able to evaluate various kinds of limits like we've done. Describe continuity in terms of limits and ways discontinuities can occur. Talk about jump discontinuities as well, for example. And derivatives, you should be able to compute them for basic examples, like I mentioned at the beginning of class, with 5x plus 4x squared or something like that. An example of the kind you should be able to deal with. Got about 1 minute for Q&A, but we can go a little later if you want. Let's hang out with the video. Let's keep it going. Does anybody have any questions you'd like to ask right now? Say it loud, but I'll probably repeat it too.
How did you get 1 up there for the asymptote?
For the horizontal asymptote?
Yeah.
I described it as these degrees are the same. So what I told you is the answer is going to be the ratio of the coefficients of the highest power of x. 1 divided by 1 is 1. But I also mentioned you should be able to compute it with the limit properties like I did on Monday. So if you're rusty on that, you want to watch that part of the video again. Anybody else? I will be available all day tomorrow between about 8 and 4. If you've got questions, just stop on by my office. See you Friday.